Welcome once again in the class of the course Water Resource Engineering. We are learning the canals. So far we have seen what are the canals, what are the types. Today we are going to see the next thing, that is what about alignment, then cross section of the canal, etc. I am Mr. S. Sogule, Assistant Professor, Civil Engineering Department. Now, fixing the alignment of the canal. So following points should be considered while fixing the alignment of the canal. First, along the alignment of the canal, the cross drainage work should be minimum. Second, the alignment of the canal should be such that the water should flow under gravity. Third, the canal alignment should be such that the quantity of earthwork in cutting should be equal to the quantity of earthwork in filling. So you might have done the road survey earlier in your second year uh, uh, in the civil course of this program of civil in second year, that is in survey course. So there you might have calculated the earthwork quantities for the road, that is for cutting and filling. So same thing is there for the canal also. So obviously in that project you have keep in mind that cutting should be equals to the filling. So no requirement of the extra murum or something for filling should be needed. So same thing applies over here. Then the alignment of the canal should be such that it can cover maximum command area. Then the length of main canal should be minimum. The large number of curves should be minimum, because of the curves the erosion problems are there. Also the reduction in the water velocity is also there. Then the alignment should not made in rocky cracked strata, because see, the losses due to seepage are more in that particular strata. So here you can see this is a longitudinal section of the canal. So these are the bed levels, and this is the earlier profile and final profile, or the bed level of canal should be like this. So the falls are like this, the water should tends to fall. This is a kind of rich canal, so that the flow up to this with some uh, required slope should be there, and then it allows to fall from that particular distance. So here you can see all the sections as you might have prepared in the case of road survey. Then these are the cross sections of the canals, like same things you might have done in the road survey also, that canal section in the part of cutting and filling. So here you can see the slopes, and this is the canal bed, and these are the berms, that is 1:1 slope has been given. Then banks are there. Then this FSL is there, that is, then freeboard has been given. So this is the part in cutting and filling. So some part has been used for cutting and some is for the filling. Now this is the section in full cutting. So here you can see this is the ground level. Here ground level is here. So this part has been filled and this part has been cut. Then you can see this is the full cutting, that is ground floor, ground level is over here, and these are the service roads, and this tola is here, these spoil banks are there, and this is the FSL for this particular uh, canal. Then this is the section in filling. So here you can see the full section has been filled, and this is the ground level. So above ground it is situated. So filling is there on the both sides, and slope here is 1.5 as to 1. So in this case you can see here this, in filling the slope is 1.5 as to 1, and in cutting is 1 as to 1. Here also it is 1 as to 1, but in this side filling it is 1.5 as to 1. So the cross section of irrigation canal. A typical and most desired section of the canal is as shown in figure, that is this. The section is partly cutting and the filling. The aim of balancing the quantity of earthwork in excavation with that in filling. Sometimes when natural surface level, that is NSL, is above top of the bank, the entire canal section will have to be in cutting, and it shall be called canal in cutting. Similarly, when the NSL is lower than the bed level of the canal, entire canal section will be in filling, that is called as a canal in filling or canal in bank. So here you can see. Then side slopes. The side slope should be such that they are stable depending upon the type of soil. A comparatively steeper slope can be provided in cutting rather than the filling, as the soil in the former case shall be more stable. So here you can see, this is the FSL, this is the silting, and this is the actual slope, that is 1.1 to 1 or 1.5 to 1. So the final slope acquired is this, half s to 1, and this is the bank. So here you can see, one horizontal, one vertical to 1.5 horizontal to 1 vertical slope in cutting, and 1.5 horizontal, one vertical, and 2 horizontal, one vertical in filling is generally adopted. In case of channels with silt laden water, the actual capacity of the channel is worked out with half as to 1 side slope, even though the flatter slopes such as 1 as to 1 or 1.5 as to 1 may be constructed at the time of execution. This is because of the fact the sides of the such channel get silted to the slope 0.5 as to 1 with the passage of time, as shown in this figure. Now the berms. Berms are the horizontal distance left at a ground level between the toe of bank and at the top edge of the cutting. So the berms are provided in such a way that the bedline of the bank line remains parallel. So if this S1 S21 is the slope in cutting and S2 S21 in filling, then initial berm width, that is S1 minus S2 into D1, that is this D1, this is S1, this is S2. Since ground level, that is NSL, fluctuates considerably, while canal bed level, that is CBL, varies very slightly. So D1 shall vary, this D1 shall vary, this depth of this particular cutting, and therefore the berm width shall vary. After the water flows in the channel for some times, the silt gets deposited on the sides, giving them a slope of 1.5 as to 1. The position of the berm therefore changes from the ground level to FSL, as shown in this figure. So here this berm has been changed from this to this, and the width become equal to this S1 minus 1.5 into y. This changes. If S2 is 1.5, that is the slope, then final berm width equals to y, that is equals to the depth of the canal. So here you can see these berms are there. So I am calling FSL, that is full supply level is meaning of this FSL, and this is the NSL. When berms are fully formed, they serve following purpose. The silt deposit on the sides is very fine and impervious. It therefore serves as a good lining and reduces the losses, leakage, and consequent breaches, etc. They help the channel to attain regime condition, as they help in providing a wider waterway if required. Even fluctuations of the discharge do not produce much fluctuation in the depth because of the wider waterway. They give additional strength to the banks and provide the protection against erosion and breaches. The possibility of breaches gets reduced because of the saturation line becomes more in the body of the embankment. They protect the banks from erosion due to the wave action. They provide a scope for future widening of the canal. Berms can be used as a borrow pit for excavating soil to be used in the filling. So these are the advantage or serving purpose of the berms. Now, freeboard, that is margin between FSL and the bank level, is known as a freeboard. The amount of freeboard, so this is freeboard has been shown over here. The amount of freeboard depend on the size of the channel. They generally provide the value of freeboard that is given in this table. That is discharge, and this is the extent of freeboard. So 1 to 5 we have to provide a freeboard of 0.5 meters. 5 to 10 we have to provide freeboard of 0.6 meter. 10 to 30 we have to provide 0.75 meter, and for 30 to 150 cumex we have to provide freeboard of zero point 0.9 meter. Now the banks. The primary purpose of the bank is to retain the water. They can be used as a means of communication and as inspection paths. They should be wide enough so that to minimize the cover of zero point 0.5 meter is available above the saturation line, as we have shown in this figure. So this is the saturation line, and here we have to provide this zero point 0.5 cover. So high banks will have to be designed as a earth dam. Now the service roads. Service roads are provided on the canal for inspection purpose and may simultaneously serve as a means of communication for remote areas. They are provided zero point 0.4 to 1 meter above the full supply level, that is FSL, depending upon the size of the channel. So you might have seen near the channels we have so many service roads, and uh, the people living in that particular area, they are using it as a communication or for the reaching of the remote areas. Then the dollars, as a measure of safety on driving, dollars of zero point 0.5 meter high as and zero point 0.3 to zero point 0.6 meter wide at the top with the slide slope of 1.5 as to 1, 2 to 2 as to 1 are provided along the banks as shown in this figure. So here this thing has been provided. They also help in preventing slope erosion due to rains, etc. So this is the road, and for protection of this thing, additional this dollars has been provided. Then the back berm or counter berms. Even after providing sufficient section for the bank embankment, the saturation gradient line may cut downstream end of the bank. In such case, the saturation line can be kept covered at least by zero point 0.5 meter with the help of counter berms as shown in figure. So this is the counter berm, because this saturation gradient line goes over here. So we have to provide this additional counter berm for this, and this distance should be zero point 0.5, as we have seen in this case. This minimum cover should be zero point 0.5. Now these are the straight uh, saturation gradient lines may be drawn with the following slopes. So the slopes has been given in this table. For clay, we have to provide a slope of 1 in 4. Then for clayey loam, we have to provide 1 in 6. For loam, we have to provide 1 in 8. For loamy sand, we have to provide 1 in 10. And for sand, we have to provide 1 is to 50 slope we have to provide. So these are the value for the type of soil we have to follow. Then spoil bank. When the earthwork in excavation exceed the earthwork in filling, even after providing maximum width of bank embankment, the extra earth has to be disposed of economically. To dispose this earth by mechanical transport, etc., may become very costly, and an economical mode of disposal of may found in the form of collecting the soil at the edge of the bank embankment itself. The soil is therefore deposited in such case in the form of heaps on the both banks or only one bank as shown in this figure. So this thing, that is spoil banks, is has been stored over here. So this is possible when the earthwork or excavation exceed rather than the filling. So these heaps of soil are discontinued at suitable intervals, and longitudinal drains are running by their sides on excavation for the disposal of rainwater. Cross drains, though through the spoil banks, may also be excavated if needed. So these are the if needed things are there, and this nothing but the storing the excess earthwork. The Borepits. When the earthworking filling exceeds the earthwork in excavation, the earth has to be brought from somewhere. The pits which are dug for bringing the earth are known as the Borepits. If such pits are excavated outside the channel, they are known as the external borrow pits. If they are excavated within the channel, they are called as the internal borrow pits. It is very costly affair to bring the soil from the distances, even it is in nearby area. These pits may cause mosquito nuisance due to collection of rainwater in these pits, and hence the external borrow pits are not preferred. So basically, this is thing that if we need the extra earth or murum for the filling, so we have to brought the murum from somewhere, so that can be brought from outside or within the channel itself. Then the internal borepits are therefore excavated from the bed of the canal as shown in figure like this. Likewise this, the borepits should start from the point of distance more than 5 meters from the toe for small channel and 10 meters for the large channel. The width of these pits B should be less than half of the width of the canal B. That is, this should be less than B, that is half width of the canal. Then these should be dug in the center. The depth of these pits should be kept equal to or less than 1 meter. Longitudinally, these pits should not run continuous, but minimum space of L by 2 should be left between two consecutive pits, where L is the length of one pit, as shown in this figure. So here you can see these are the that B is there and L is there, and this is that L by 2, that minimum space should be kept in between. This is all for today's lecture. These are the references. Thank you.